Editor's note. Yeah, I did realize that I was mispronouncing carbonyl. It's actually pronounced carbonyl and not carbonyl. That's the British pronunciation, so sorry about that. Hi everybody, in this video I'll be discussing imines and how they form. So this will cover the reaction mechanisms of both major methods of imine synthesis, catalyzed and uncatalyzed, and I hope you'll learn something. Without further ado, let's see the actual mechanisms and hopefully learn some things about imines. So, first, what are imines? Imines are compounds of primary amines and carbonyls. They can be formed with or without a catalyst, as you'll see. On the top, I just put R groups where everything would go. Secondary amines form compounds called enamines, like this example with cyclopentanone and pyrrolidine, which we will not be discussing here. And tertiary amines do not react at all. Next, we'll see some useful reactions of imines and why you'd want to use them in the lab. So, here are two common reactions of imines. There's others that I'm not really going to account for here, but these are the most significant ones that you will probably need to know. So on the top, we have reduction by hydride reducing agents like sodium borohydride and lithium aluminum hydride. This can either be done with a pure sample of the amine, or it can be done in the pot of the reaction. The combination of forming imine and then making an amine out of it by reduction is called reductive amination. It's a pretty common reaction in the lab. That's a whole topic in and of itself, and one that I don't really feel like I'm going to delve in here, or the video would be an hour long. So the second reaction on the bottom is hydrolysis. So imines can be hydrolyzed to carbonyls again, and happens relatively easily for some imines and less easily for others, which causes imine syntheses to be reversible, as you will also see. We're not going to discuss that mechanism here, but maybe in a future video, who knows? So now let's just see the mechanism of the reactions already. First, we're going to look at uncatalyzed imine formation, which is directly between an amine and a ketone with nothing but a solvent. The first step in the mechanism is attack on the carbonyl by the amine. Only some amines can attack unprotonated carbonyls. We'll discuss this selectivity later. This forms this intermediate compound, where the charge on the nitrogen is 1 plus and the charge on the oxygen is 1 minus. The intermediate compound is pretty unstable and almost immediately goes a proton transfer. The oxygen on the left abstracts a proton from that nitrogen over there, forming this intermediate compound called a geminal amino alcohol or carbanolamine. In the final step of the uncatalyzed imine synthesis, the carbanolamine expels water. This is favored due to the higher pKa of the nitrogen relative to the oxygen and the higher nucleophilicity of the nitrogen relative to the oxygen. I've included the lone pairs in this diagram so you can see. The elimination is concerted and it all happens in one step. Hydroxide is expelled, which then picks up the proton, forming water and the imine. Now, let's see some examples and the selectivity of the imine synthesis uncatalyzed reaction. So, this reaction works for both aldehydes and some ketones. We'll discuss that more on the next slide. On the top, we have aniline and benzaldehyde reacting to form N-benzylidine aniline, and on the bottom, we have the imine of acetophenone and aniline forming. This reaction is mainly used to form oxenes. On the top, compounds of hydroxylamine or its O-acyl derivatives, like acetoxine here, which I've got forming from acetone and hydroxylamine. It can also form hydrozones or azenes, which are compounds of hydrazine derivatives. This includes substituted hydrazines like phenylhydrazine or acyl hydroxides like semicarbazide. Here, benzaldehyde and hydrazine are used. This can form either the azene, which is the product of 2 mole equivalents of carbonyl and 1 mole of hydrazine. Here it's called benzalazine. Or the hydrazone, formed from 1 mole carbonyl and 1 mole of hydrazine. Here it's called benzaldehyde hydrazone. Why do these two things work particularly well? Well, that's because hydroxylamine and hydrazine are more reactive. If you know, hydrazine is used as a rocket fuel, and free-base hydroxylamine is pretty unstable. The main issue of imine formation without a catalyst is that most carbonyls, there are some exceptions, aren't strong enough electrophiles to react with most amines. Small amines like methylamine do react though, as do more reactive aldehydes, i.e. benzylaniline from benzaldehyde and aniline, that's benzylidine aniline also. Hydrazine and hydroxylamine are relatively strong nucleophiles. This part is so cringe and I cannot believe I wrote it. So what can we do, Zenzacubic-san? Well, yeah, that was pretty cringe and I can't believe myself. But back on topic, we can use an acid which protonates carbonyls, making them a little more electrophilic. Here I have cyclohexanone, reacting with methylamine to form N-cyclohexyladine methylamine, or cyclohexanone methylamine. This method is mainly used for ketones or less reactive amines. So now, let's see how this works, shall we? First, the carbonyl compound is protonated. Even though I already said carbonyls are electrophilic, they're nucleophilic enough to accept protons from acids. For example, here I just have a generic one, like the last mechanism example. The next step is similar to the first step of the last mechanism we just saw for the uncatalyzed reaction, except instead of here, the starting stock being a ketone, it's the oxocarbenium ion, which is much more electrophilic than a carbonyl, unprotonated. So it is easily attacked by the amine, which opens the double bond, forming this intermediate compound here. The oxygen is charged neutral as a hydroxyl, while the nitrogen is protonated as an ammonium compound. The next step is proton transfer. As in the uncatalyzed mechanism, the oxygen abstracts the protons from the ammonium cation, in this case forming hydronium. Hydronium, being the excellent leaving group it is then kicked off by the nucleophilicity of the nitrogen. This forms an iminium cation. And in the final step of the process, the iminium cation's proton is abstracted by a solvent. I've much simplified it here, just showing the loss of H+. This is favored because iminium cations generally don't like to exist, and are also intermediates in the hydrolysis of imines, which, again, I will not discuss here. So, thanks for watching, and make sure to like and subscribe. Here's me as a molecule. Cyclopropanes look like cat ears. Nice, huh? Bye. God, I love my chair. Makes this so much more fun.